Hello, this is Dr. James Camp from Lee College in Baytown, Texas, and these are my comments on classes in C++. This is based on the Chapter 13, Introduction to Classes of Starting Out with C++ by Tony Gaddis, but has some serious edits by me in some places. Okay. So first off, what is this whole big deal about object-oriented programming? Procedural programming, which is what we've done prior to this point in this class, focuses on the procedures, the process or actions that occur in a program. Procedures is a general programming term. They're called functions in C or C++. They're discrete sets of actions that you can optionally pass data to and from, but it's the procedures that take center stage in procedural programming. Object-oriented programming refocuses on the data and the things that the data can do with itself. The data and how it's operated on is how Gaddis puts it. Objects are structured data types that include both the data you want to represent and methods that operate on them. Okay, so to illustrate the difference, here are the procedural and object-oriented approaches to simulating the flight of a projectile. Let's say that you have a round projectile flying through the air. It's got a certain drag, it's got a certain lift coefficient. Of course, it has mass, and so it will be affected by gravity. So you would first have to define the data that you want to model. You've got mass and diameter, coefficient of drag, coefficient of lift. You might define those as constants up at the top of the program, or you might have those as parameters that the user enters into the program every time you run it. You would also have to track, if you're talking about the flight of a projectile, its x and y position and its velocity in the x and y components. Okay, so in order to do this, at each point in time, you'd also have to track, forgot to put that in there, but you'd have to track time as well. At each point in time, we need to know what all the forces are on this projectile so that we can calculate what happens to the velocity and the position. So we'd need to define functions such as f of g, force of gravity, force of drag, force of lift. Some of these would be fairly simple functions. Gravity just depends on your mass, but drag depends on mass, area, drag coefficient, and current velocity. We'd have to have a function that sets the initial velocity of the particle, though we really could just write the equations, v naught sine theta and v naught cosine theta. But it's more of a procedural programming thing to have a function that does that. And then at each point in time, we need a function that uses all of these force equations that we've come up with to calculate the next time point. And note that if we want to set an initial velocity, if we want to set more than one parameter in these functions, we have to use all of these pointers to pass references to our variables so that we can pass the correct information back to the function. So, or back to the calling function. So this is how this might play out in a procedural example. You've already input from the user x0 and y0, the initial position, and you're setting time to equal 0. So we set our initial position, initial position and time, We set the initial velocity based on a launch velocity and a launch angle. And then we go into a do while loop. We'll calculate the next point, get the thing off the ground, and get it flying. At each point, we're going to have a new velocity, a new position, and a new time. So all of those have to be passed as references. And we're going to continue that while y is greater than 0. We're presuming that we're not launching it from down deep in the ground or something, right? So y should always be greater than 0 until, boom, it hits the ground at the end. And then at the very end, we can see out final distance equals, and we've been updating x constantly in this calc next point function. So x should now be the full distance that the projectile traveled. Okay, that's the procedural way. That set of code should be fairly comfortable to you if you've been following this class fairly well. An object-oriented simulation would go about this quite differently. We would define an object called projectile, which had properties: mass, diameter, coefficient of drag, coefficient of lift, and methods: launch, fly, and then set and get methods for x and y. So in this setup, we would still have code that calculates gravity and drag and lift and next point and initial velocity and all of that, but it's hidden. It's built into the object so that the basic code says we create a projectile called proj. We set its x to x0 and its y to y0. And then, kaboom, we launch it. We tell it to launch with velocity v0 and launch angle theta, and it will update its internal understandings of velocity and position to account for that. And then we call projectile.fly, and it's now going to do its own little internal calculation loop, which might look exactly like my calc next point function, or it might be different. I don't care. As the person who's writing this basic program here, somebody, probably me, but somebody is going to have to program the fly code into projectile, but the point is it's built into the projectile. And if I come up with a better way to simulate it, then I can just change that one little bit of projectile and it doesn't affect my program at all. And then at the end, I say cout final distance equals projectile.getX. Okay, at the end of my flight, projectile has stored its x value somewhere. Where, I don't know. It's internal, it's hidden, I don't care. I just know that I can get that x value from the object and report that as the final distance on my simulation. Okay. That's dramatically different from the procedural example. We're doing operations on an object, setting things, launching things, and then letting it fly. And then finally, we're just getting the results from the object. For one thing, it actually makes the code much, much more readable to the average person. The procedural code over here, next to impossible for your average person who isn't a programmer to even wrap their mind around. Whereas projectile.set, projectile.launch, projectile.fly, those are pretty simple concepts to wrap your mind around. It looks like a fairly logical way to do this simulation. And if you write your projectile object sufficiently well, it's almost a self-documenting kind of thing. It's pretty obvious what's going on in this object. Okay, so Gaddis wants you to know that there are some limitations to procedural programming. If data structures change, sometimes the functions have to be changed with them. If I'm passing a data structure and a description of that data structure to my function, and I change the data structure to include the description, or I change the description to be its own little structure or something, I have to change the function. I have to rewrite the whole function to do that. If I change how my object is internally representing its data, that doesn't change at all how the calling program works. In procedural programming, data often must be passed back and forth. So you have, in the typical situation in C++, you have main, and you have, function calc something. Main has to pass its data up this way to calc something, and then calc something has to return that data back to main. Whereas if I had an object, I set the data, I tell the object to do its calculation, and it does it internally. It doesn't have to have all this data passing back and forth. I don't need all the pointers and all of those things that become common in fairly complex functional or procedural programming. Programs that are based on complex function hierarchies are difficult to understand and maintain. So if you think back to the previous slide where I showed you that program where the main function calls get next x or get next position or whatever, and that's going to call all of these force equations, and it's easy to lose track of where in the program a particular thing was set up, where it's being used, and that makes those programs difficult to maintain. Whereas if you build a program entirely out of objects, you can break down, well, I told the object to do something and it didn't work the way I expected, so it must be the code that's internal to that object that needs to be debugged. Difficult to modify and extend. Functions are typically written to do one thing, and they are typically written to do that one thing pretty well, but then to modify the one thing that they do or extend it to do something new may require writing a whole new function or perhaps even restructuring the entire program. And these complicated function hierarchies are easy to break. If one thing goes wrong in one part of the program, it's often hard to figure out, to trace that down and debug it. Okay, so now that I've sold you on object-oriented programming, what's the terminology? There are two words that we're going to use in this presentation that you may think are kind of interchangeable, or at least you're not sure what the difference between them is. A class is the type that an object belongs to. It's like a struct in that it allows bundling related variables. Okay, so you can have class student who has a name and a number of credits at the school and a GPA. Okay, you could represent that as a struct, you could represent that as a class. The difference is that a class adds some concepts. Data privacy. Some data is only visible from within the class. So credits and GPA may not be something that the that any user could just go in and change. Those may have to be accessed through specific secure ways. They add member functions that set the data, get the data, operate on the data. And they add static members that belong to the class. We're not going to talk about that in this presentation. I think that's reserved for the next chapter in Gaddis's book. But you can have a student.school that belongs to the whole class student. Any student I'm dealing with is going to the school Lee College. It doesn't have to be set on a per student basis. The other word we're going to use is object. And an object technically is an instance of a class in the same way that a variable is an instance of a struct or an int or a string or whatever else. Okay, so one way that people typically say is that a class is like the blueprint and objects are the individual houses made from the blueprint, or a class is like a recipe and individual loaves of bread are the objects. There are a number of metaphors that people use for this. Some more terminology. Attributes or properties are what we call the member data of a class, because we're assuming that the class is simulating an object. And objects in the real world we don't say that they have variables. We say that they have attributes or properties. A tree has a height and it has a color, green most of the year, maybe red in the fall. And you know, those are attributes or properties of the tree. These classes or objects also have methods or behaviors. These are the member functions of the class that do things for us. So sometimes behavior is appropriate. We can talk about what does a tree do? It does photosynthesis. So we could call tree.photosynthesize. We could call tree.sway in the wind. Those are behaviors. But a lot of the methods that we call are not so much behaviors of an object as just accessing that object. So we could call tree.getHeight. We could call tree.setSeason, and that would change it from its green color to its fall color, or make it lose its leaves in the winter or something like that. Okay. There's also a concept called data hiding. Okay. The formal word for this is encapsulation, which is restricting access to certain members of an object behind what we call a public interface, which are the members of an object, usually methods, not attributes, that are available outside the object. And the advantage of a public interface is they allow the object to provide access to some of its data and functions without sharing all of its internal details and design. I mean, if you're into the open source movement, you don't care about sharing your design, but you know, maybe you want to make some money off the object that you've written. Well, you don't want to share with the world exactly how it works. Provides some protection from data corruption. Also, not sharing all of your internal details means somebody can rewrite the object to upgrade its functionality, and that doesn't change how everybody else interacts with it. Provides some protection from data corruption and invalid data. So I couldn't set a negative length for a rectangle, for example. And it allows for events to be triggered whenever private data is updated through one of my public functions. So if I have a my student object and I update the number of classes he's successfully completed, then that might trigger a recalculation of his GPA, okay? Because I won't remember that I need to set his GPA every time I set the number of classes he's taken. Okay, so let's get into classes. One little side note that I added to this presentation, C++, the original name of C++ was C with classes, okay, which I think is not one of the more catchy names for a programming language, but I think C++ was a much more of a winner of a name. But the idea was that this programming language was supposed to be basically C with the extension that it has all of these object-oriented class-based extensions. So most of what we've learned prior to this lecture right now today about programming in C++ can translate right over to old-fashioned C with just some minor changes. Those changes mostly have to do with the fact that you can't use string objects in C because it's not object-oriented, and you can't use stream IO operators like cin and cout in old-fashioned C because they're also object-oriented. So you have to replace your strings with C strings and your IO with printf and scanf. But if you can get around those minor changes, our if loops and our function definitions and even the pointers that we've learned about recently are all things that were carried over to C++ straight from C. What you learn about classes and objects in this lecture is the main reason for the existence of C++ as a new language. The people who created C++ strongly felt that they just couldn't do what they needed to do with a programming language unless you could add object-oriented programming to it, and that's why C++ was born. Okay, so objects are created from a class. Okay, the format for declaring a class, you can think of it as a class of objects, like tree is a class of plant and car is a class of vehicle, you know. Well, class, you define a class by typing out the keyword class and then a name for your class, typically given in uppercase, starting with an uppercase letter. Open curly, declaration, 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 close curly, semicolon. Looks really familiar if you paid attention to the last lecture on structs. Okay, where we start to see some differences, this private and public keyword, we didn't see that in structs. And then we have member functions here that do things. Okay, set width, set length, get length, get area. Okay, all that is new, and we'll try to cover it as we go through. Okay, so first let's talk about the public and private. These are called access specifiers or access modifiers. They're used to control access to members of the class. If it's public, then any code outside of the class can access that member. So that's usually reserved for our member functions, our methods that we've written to be public. Private can only be called by if it's a function or accessed by if it's a data member by functions that are members of the class. And we typically make all of our data private because we don't want some bozo out there changing the length of our rectangle without us knowing about it. Okay. Yeah. Access specifiers can be listed in any order in a class. You don't have to put your private stuff first and your public stuff second. They can appear multiple times in a class. So you can have a private section, then a public section, then another private section, then another public section. And if you don't specify, if it's not following a section label, the default is private. So with the rectangle that we've defined so far, we could have left the private declaration out on those first two, and C++ would make them private by default. But that's kind of sloppy programming. It's better to specify what you want to happen with each of your elements. Okay. It is possible, I'm usually too lazy to do it, but it is possible to put the const keyword after a function that does not change your object. So get width and get length obviously are just getting values from your function, so they have no reason to change the function, so they are defined as const functions. When you define a member function, what is typically done is that you put the prototype, so int set width double, in the class declaration, and then later on outside the class declaration where you have a little more room, you define the function using the class name rectangle, the member function name set width double W, okay, and then you join them with the scope operator, colon, colon. We've seen that at the very beginning of the class when we saw standard colon, colon, cout, for example, before we learned to type using namespace std and not have to worry about that anymore. That means that cout is in the scope of the standard library. Okay. Well, this means set width is in the scope of the rectangle class. Okay. We talk about functions, two particular kinds of functions, member functions in C++ programming or in any kind of object-oriented programming. A mutator function mutates your object. It changes the object in some way. These are often more colloquially called setter functions because they often begin with the word set. Set width, set length, set number of exams in my course, whatever. Okay. An accessor function accesses data from your private members. Okay. They're colloquially often called getter functions because they usually begin with the word get. Get width, get length, get exam average, whatever. Accessors by default do not change an object's data, they just access it, so they should be marked with that const keyword. Okay, so now that we've written our class, how do we define an object that is an instance of that class? An object is defined just the same way a variable instance of a struct is. You use the class name as the variable type, and then you give your variable a name. Rectangle R. How original. Okay. Access members using the dot operator. R dot set width 5.2. Cout, extraction or insertion operator, R dot get width. Okay. So that function's just like any other function. You call it, it returns its value to that position in the code, and that value gets passed to cout. If you attempt to use private members using this, if you typed r.length equals 6, you'd get a compiler error for accessing private data in a public fashion. Okay, this shows our full rectangle, the first version. Note that we have the function prototypes here, and then we have full declarations here using that scope operator to let the compiler know that it belongs to the rectangle class. Okay, and note that our get area doesn't actually get a value. It takes the width and the length, multiplies them together, and returns that value. So it's getting area, but it's getting it by doing a calculation. There's nothing at all illegal or even unusual about doing that in object-oriented programming. Okay. And in fact, here we have a comment on why that is. Some data is the result of a calculation. In our rectangle class, the area of the rectangle is calculated as length times width. Okay, that's how you calculate a rectangle. If we were to use an area variable here in the rectangle class, its value would be dependent on the values of length and width. But what if we changed length or width without updating area? Then area would be what we call stale data. It no longer reflects the current, the freshest state of the object. So to avoid stale data, there are two approaches that programmers take. One is to calculate the value of that data freshly each time it's accessed using its getter function. Okay, so get area doesn't look up area, it just takes length and width and multiplies them. Or we could have an area variable with an area attribute within the class, but calculate its value every time length or width is updated. So in our set length, instead of just saying length equals L, we'd also then say area equals length times width. Okay, we'd calculate that freshly each time length or width is updated. Which one do you choose? It sort of depends on how computation intensive this calculation is. For length times width, that doesn't require much of a workout on the computer's part. So just calculating length times width every time someone calls get area makes sense. But what if I had 100 students in my class and I wanted to take the average score and the standard deviation of their data? That's a fairly computer intensive calculation. So it might be better to calculate that value once every time a student is added or updated every time a test score is added or updated. Just calculate it once and then have it as a variable that can be gotten with the getter function, rather than to calculate it freshly every time somebody tries to read the average. Okay, so it depends kind of on how computationally intensive this is for you. Other ways to create instances of an object include creating a pointer to an object. Okay, so rectangle star R pointer is currently being set to null pointer, but then just like we did with structs, we can make R pointer equals and other rectangle. So we're now pointing to this other rectangle. We can use the arrow operator to access the set length function. We can use the arrow operator to access the get length function and pass that value to cout. We can also use a pointer to dynamically allocate an object. So you can say star rect pointer equals null pointer, but then rect pointer equals new rectangle. Okay, so we've just created a new rectangle in the vast wilderness of our program's memory and assigned it to rect pointer. Okay. Now, a little bit of the rationale for why we have private members. Why do we do this data encapsulation business? It may seem odd after you've worked with structs for a while where all the data is public. It may seem inconvenient to have to use these getter and setter functions. But when data can be accessed only through public functions, those functions serve as a sort of protective gateway. Okay. One example of how that might work, making data members private, provides data protection. We can verify and validate how our data is accessed and set through the getter and setter functions. You might have to provide a user ID to the get function before you look up a student's GPA. You might have to, the object itself might need to validate that the GPA is between 0 and 4, or that set diameter in this case might need to check for and invalidate negative numbers because you can't have a negative diameter. So if you try to set a negative diameter, it could return an error. It could just keep the old value, whatever that was, and reject the negative number. There are a lot of options here, but you can invalidate that negative number. Mutator functions can also trigger events within the object. MyCircle.setDiameter should not only update MyCircle.diam, but should also trigger recalculation of MyCircle.area, as we talked about a minute ago. Or MyGradebook.setGrade should trigger a recalculation of the grade average. Okay. All of these public functions, the things you can actually access publicly, define what we call the class's public interface. So you can interface with setWidth and getWidth. You can't directly access width itself. So we can, in fact, model a class two ways. You can write a complete model of the class for programmers, which is mostly of use to the programmers writing the class, okay, which tells you what the private members are and what the public members are. But there's also the public interface, which is what's published for programmers who are just using the class. Okay, those people don't need to know how you're storing length or width, whether you have an area variable or not. They just need to know what the names are of the setter and getter functions that they can call. Okay, and that's called separating specification from implementation. Another way you do this in practical C++ is to place the class declaration in a header file, okay, and then the function definitions, the actual source code, in a .cpp file that's separate from your main CPP file. Okay, the program that uses the class will then pound include classname.h, okay, and classname.h has to be, and classname.cpp has to be compiled together with main program.cpp and linked together. Often the header file, often this is done in such a way as part of what's called a class library, where the header file is made public, but the code file is distributed as part of a compiled code library, so that nobody can get in and change your code for how your object works, but they have the headers that they need to access and use your objects, your classes. That is how almost all of these programming frameworks for writing graphical interfaces are distributed, is as kind of compiled code libraries, like Microsoft's .NET library that I've used to write a few graphical programs. You don't have to separate your member functions from your from your class definition. You can, in fact, put an entire member function definition on one line if you want to. Int get width const return width. Okay, and that we can include in the main body of the class definition if all of our functions are so simple as the ones in this rectangle. So there's no need in this rectangle to separate out rectangle : get width and write it out somewhere else, because it takes like a line and a half, right? So that still keeps your class definition short and sweet, but keeps everything together in one place as well. Okay. Constructors. Okay, let's take a deep breath. We've now learned how to write, to specify a class. We've learned how to make objects out of our class. What we haven't learned is that there's an easy way to set the values of your object right up front when you make that object, called a constructor. It's a member function that is automatically called whenever a new object is created on a line of code. The purpose is to construct the object, and usually there are two options. There's what's called a default constructor, which doesn't take any parameters and just initializes out your values to something sensible. Okay, we're going to create our default rectangle to have no width and no length because we haven't specified anything. But there are typically also overloaded constructors that take parameters. So in this case, I can provide W and set width to W. I can provide L and set length to L. And now instead of having to call rectangle r.setWidth, r.setLength, I've set it all up in one line of code. It's very handy. Okay. Here's their code for the default constructor. Note that a default constructor does not have a return type. There's nothing over here, not even void. If you were to write void rectangle : rectangle, the compiler would throw an error at you. Okay, and note that also in this version 3 of their rectangle.cpp, they've expanded on the set width so that it's got a data validation function. Okay, like I was talking about with the my circle might want to not have a negative diameter. Well, this is saying we can't have a negative width. So it'll see out invalid width and exit the program. That's kind of harsh, but that's what they decided to do. There's usually a more elegant way to handle an error than just quitting the program, but who knows? In C++ 11 or later, which is what most of your compilers will be using at this point, it's 2020, hopefully in 9 years they've all updated their code, you can initialize a member variable in its declaration statement. So instead of providing a default constructor that sets everything to 0, you can just set double width equals 0 right here in the class definition. That's known as in-place initialization, and it basically takes the place of your default constructor. Okay. A default constructor is one that takes no arguments. If you write a class with no constructor at all, C++ will create a default constructor for you, and it will do nothing. Okay. If you simply create an object on a line of code by saying rectangle R, okay, that calls the default constructor. It's as if you wrote rectangle R with parentheses and no parameters there. If you want to pass, say, a width and a length to your rectangle constructor, you call it this way. You write rectangle R parentheses 10.5. Or if you're doing dynamic allocation, you can say rectangle star R equals new rectangle 10.5. Okay. Either way, we're creating a new rectangle object and we're populating it with width 10, length 5. Now, be aware you can only do this when you create a new object. You cannot later on say R 10.5 or R equals 10.5. Nothing like that is going to work. It has to be done at the moment that you create the object. That's why it's called a constructor. You can write a constructor that does both the default constructor job and the non-default constructor job. So we could say rectangle double width equals 0, double length equals 0. And what that says is that if nobody passes any parameters, we treat them as 0. If somebody does pass parameters, we go ahead and set. So again, typing rectangle R on a line of code just acts as if you had typed R of 0, 0. Okay. When all of a class's constructors require arguments, okay, if you have not written a default constructor, then you must pass arguments to the constructor when creating an object. Okay. So if you're ever going to imagine a situation where you're not wanting to pass arguments to the constructor, be sure to write a default constructor for your object. Okay. Not as important, but certainly important is the idea of a destructor. If we end up creating any memory as part of the construction of our object, then the destructor should delete that dynamic memory. So an example here is in this object inventory item, they haven't pre-allocated a string for the description. They just wait until somebody passes them a description in the constructor, and they say new character of string length description plus 1. So we've just created a block of memory. It's sitting there until we get to our destructor here, and it says delete description. So that will cross out that memory and free it up to be available for some other object or some other part of our program. When a new object is dynamically allocated on with the new operator, its constructor executes, like we saw on a previous slide. When the object is destroyed, its destructor executes. So if I type delete R, it's going to run the destructor object to try to free up any memory before R goes away. Okay. I mentioned this already. You can overload constructors. So you can have rectangle with a single parameter, rectangle with 2 double parameters. Maybe the rectangle with a single parameter sets up a square that has the same length and width. This inventory item here, you pass a string description in one that sets description equal to desk. Okay, and you pass nothing in the default constructor, which just sets description to a blank string. And then in the third one, you pass a string descriptor and a cost and unit, so all of these get set. So you get to decide when you create your object how much of that information you want to provide right away. Okay. There's also a cool thing called Constructor Delegation. If you have 2 constructors that do essentially the same thing, but one of them sets just null values and the other one sets actual values, Constructor 1 can call Constructor 2 with a bunch of blank values. And the way you write that is contact the default constructor here, colon, contact with 3 empty strings. Well, that's going to refer to this string, 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 and it's going to call that version of the constructor for you. You must not provide more than one default constructor for a class. And when you do that, remember that a constructor that has default arguments for all parameters counts as a default constructor. So this code will not compile because both square and square int equals 0 count as default constructors, and the compiler gets confused. While we're on the topic of overloading, Member functions can also be overloaded, so you can have set cost with a double and set cost with a char star so that you can pass either a numerical value or a text string that somebody typed in and you want to process it to come up with the cost. As with any overloaded functions in C++, they have to have unique parameter lists. You can't have two different doubles. Set cost double price and set cost double net price or something. That won't work. You have to have different parameter lists. Okay. It's possible to write private member functions. So that example I started us off with that calculated the trajectory of a flying projectile probably had several internal private member functions that calculated drag and lift and total force and acceleration and all of that stuff, probably calculated internally by a series of private member functions. They're not part of the public interface of the class. They're just there to serve internally and get called from other member functions. Okay, now onto something a little more interesting. You can create arrays of objects. Okay, so if I, once again, it's handy to be able to work with one thing, but it's much more handy to be able to work with a lot of things. So maybe I want to throw not just one projectile, but a dozen projectiles. So I create an array of them. Or I don't want to just deal with one inventory item, I want to have 40 inventory items. When the array is defined, unless you specify otherwise, the default constructor for the object is called. You can invoke the constructor by using an initializer list as if you were creating an array of ints or an array of strings or an array of whatever else. However, that only works if the inventory item only has one variable in its constructor. If you need to call something that also has, say, a price and a number of items, then you have to call the entire constructor function in the initializer list, which is really damned inconvenient, but it works, and that's what we got. And you can mix different constructor calls. Hammer can be called without a price and a number, but wrench can be called with a price and a number. Objects in an array are referenced using subscripts followed by dot notation, just like an array of struct. So inventory at subscript 2 dot set units 30, inventory at subscript 2 dot get units. We'll look up the number of units and then pass that to cout. Okay, this gives you an array of inventory items, and then for int equals items num items, we call get description, get cost, get units. Sometimes you don't want to allocate all the objects in an array at once. Okay, you might have an array of 100 inventory items, but you only have 20 inventory items on hand. Why waste the memory on the other 30 or the other however many? I can't add today. You might have 3 rectangle pointers, but only the second one needs to be defined right now. So rectangle pointers at 1 gets to be a new rectangle with length 10 and width 20. So other times you just want an array that points to objects you've created elsewhere in your program. I've done a simulation recently of the COVID-19 virus where I simulated a social network, and rather than making lots and lots of copies of people, I wanted each person to point to their friends. Okay, and so you need an array of pointers rather than just a straight up array. So you create that by saying rectangle star rect pointers of 3, and then you allocate a new rectangle that just allocates pointers. It doesn't create any new rectangles. So rect pointers at 1 equals new rectangle of 10 and 20, and then you access it using the arrow operator. Rect pointers at 1 pointer get area. Rect pointers at 1 arrow get area. We'll find the area of that rectangle and pass it to cout. Okay, that's all the programming we've got in this lecture. There's one little bit left, however, that you will see UML diagrams of classes sometimes, and so you need to be able to know how to write them and read them. Okay, UML stands for Unified Modeling Language, and it's just a set of standard diagrams. It's not actually a language, it's a graphical language for depicting object-oriented systems. So the basic UML diagram has a 3-box stack. The first box gets the class name, the next box gets the member variables, and the next box gets the member functions. So for our rectangle that we keep coming back to, it would look like this. But how do you know which things are private and which things are public? Well, we add minuses in front of the names for private members and pluses in front of the name for public members. Okay, well, what about data types? We add a colon and a data type, so it's almost backwards of C here. Instead of putting double width, we have width colon double. Same thing for parameters within a function, same thing for return values of a function. So basically, we have 2 doubles, width and length, that are private, and then we have 2 void functions, set width and set length, that take doubles, and we have 3 double return value functions that get a width, get a length, and get an area. And those are all public functions. How do you define a constructor? Well, the constructor has no return value, not even void, so it just ends with a colon. Okay, otherwise it looks exactly like any other function definition. Okay. So that wraps us up on everything you need to know to get started with object-oriented programming in C++. I'm sure I'll have some assignments for you to practice that coming up. And then we have another lecture coming next week on kind of advanced object-oriented programming. So look forward to that and stay tuned. Keep learning, keep studying, keep in touch. Bye-bye.